Hi guys, it's now a while ago that we did a so-called performance upgrade of my Powerwall, and that video did not have a happy end. It ended with an unsuccessful startup of the controller, so the controller kept resetting, and it took me a little bit to understand what the problem was, and everything ended in a quite long waiting time for so many things. So that this video is now actually done almost a month later. There's also an interesting point. It actually inspired me to create a new product. Well, not a new product by itself. We will talk about this in the second part of the video. To understand the issue, what caused to this unhappy ending last time, for that we have to look a little bit to the beginnings of this Powerwall and understand how this controller and all its peripherals, its sensors, etc. is powered. Right, so from the first version of this controller board, I always did the same thing, right? I took the main DC voltage from the battery bus here, so a voltage between 50-55 volts, and converted this down to 9 volts DC. And with those 9 volts coming out of a high voltage buck converter, I went into the Arduino Mega Pro board. On the Arduino Mega Pro there are 2 voltage regulators which are creating 2 different voltage rails. One is a 5 volt rail and one at 3.3 volts. So every modern microcontroller will use one of these 2 voltages to operate, and you can also take those voltages and power your peripherals. So after I've added another display and especially a bigger relay board again to this, which are all running on 5 volts, it actually caused a breakdown on the 5 volt rail, right? So it was not enough power anymore created that way directly on the microcontroller board. This caused the controller to crash, and it crashed always somewhere else, so that made the situation a little bit difficult to understand, because sometimes it crashed when it tried to read a sensor, sometimes it did not start up at all, and then it crashed when it tried to pull relays, etc. like this. And that was the final clue for me then, and I knew, okay, there's not enough power available here to run this controller anymore. So the only thing I had to do is I had to externally power the relay board. They typically have the option to do so. Now I have 2 buck converters inside there. One is still making my 9 volts for the controller board, and the other one is making 5 volts for the relay board directly, and everything works fine. Unfortunately, this collapse of the 5 volt rail damaged also some of my peripherals. You saw already the OLED display, that one was damaged, I had to replace it. Another thing was the shunt, my current sensor, that one was also damaged, and that one was especially an interesting story because I could not replace that sensor anymore. I ordered it 2 times from China, I could not get it here in Thailand, and all those boards which came from China had a fake chip on them, and they did not work, so I had to dispute. I got my money back, I ordered the next one. And every time you order something, you have to wait 2-3 weeks, and then at the end I always had a non-working board in my hands again. So I switched back to the previous sensor, which was the INA 219, and this is now again back here in the Powerwall. I also changed my shunt. The shunt was a 100 amp shunt. And because this Powerwall is now actually running almost 100 amps, it got really hot. It already got very hot at 60 amps, but especially with, let's say, 85 amps, which I typically have here at charging, it got really hot, so I have switched it to a 150 amp shunt, and that one is of course not getting as hot as the other one. The sensitivity of the shunt is reduced, of course, but that does not really matter. The sensor is very sensitive, so it's still good enough. So let's check what we have done, and I will tell you a story to each of these and how everything works. But let me first say this: the performance upgrade of this Powerwall is not just what we have done here on the Powerwall. A big part of it was also the latest solar array I have done here on the parking behind me, because that one, without that new solar array, the new components like the new charger would not even have the power to operate itself, because there would not be so much excess on that phase anyway. So this has to be considered also as a part of the performance upgrade. But now everything is working fine. The Powerwall has been charged and discharged fully every single day. It is running now stable. That means around 16 kilowatt hours every day have been charged and discharged from this Powerwall. And every day, almost every day, at around 2 p.m. the Powerwall, the cells have been again fully charged. So there's a lot of reserves now still here, because everything is going much faster and much more powerful, charge and discharge. So this gives us a little buffer also for a cloudy day, or later on during the rainy season, when the clouds are then covering the sky, maybe from 2 to 3 o'clock afternoon. And until then, typically the battery should already, even if there's guests in the hotel here, should then already be full, and we have a lot of power available then for the night. Okay, so let's open some doors here, and I will tell you a short story about every device which was installed and if there has been some problems or not. Let's start in our newest compartment here. Here we have a new 2000 watt inverter and our variable charger. I don't need to say much about the inverter. It has a soft start, everything works perfectly. There was a problem still with it, which I will talk about when we're talking about the BMS. The charger, you saw it already in another video, works really well. But another thing about this so-called intelligent charger, so the designer of this device used some of his intelligence to fulfill a certain task. But this sort of intelligences of other people, they not always fit into your own idea how you want to do something, right? And what I did not mention in the video about this charger was that it actually limits its output when the voltage is on the battery is low. So it does not really like to output full power on a low battery voltage, which might be a good idea, but in this case, when you have a really huge battery pack, that does not matter at all if this is outputting now 10 amps or 30 amps, because you know, when you have several hundred amp hours of battery capacity, that's still very low numbers. So I had to implement a sort of soft start for this charger as well. So every time when the voltage is low, I'm limiting the charger to a certain amount. I'm starting at 10 amps, and when then the voltage is in a different range, a little bit higher, I go to 15 amps, and then above some certain voltage, I then let it output the full power. And this works now very nice. Before I did this, the charger would kind of freak out sometimes when it had to output a lot of power and then was turned down. And okay, here in the next compartment, the battery cells here. And if you have seen other videos from before, you can now kind of see that this is now much more organized. And the main reason for this is that the cell monitoring, which I was doing by myself, is not here anymore. This was the third sensor which was damaged due to the unstable power rail. I decided to remove it because this can all be done now by the BMS anyway. I can look into the cells here with the app from DALI, and yeah, it's not necessary to have a separate cell voltage monitoring, because this one is of course much more exact anyways. There is a story to the BMS. This is the second smart device which was added to this Powerwall with the last upgrade. And also here I must say, when do you call something smart, right? They are calling these devices smart because you can use now a phone and you can look into it, you can set all the limits, etc. But at the beginning, every time when my inverters have started, the BMS shut down the circuit, right? And this was even when I was setting all the limits to the maximum range, etc. So I did not set any narrow values here. It just shut down on me when the inverters started. So obviously a limit has been reached somewhere or breached, but now I have to complain. Why do you call something smart if it cannot even tell you why it has shut down on you? So there is no log given to you when you look into your app why this BMS had shut down on you. And even when I was watching my app during the inverter starting up, there was nothing visible, because that problem must have just existed for a very, very short time. But it was enough to shut down the MOSFETs inside this BMS, shut down the circuit. But still, I did not know why this was happening. So I could only have a guess, of course, and of course when the inverter start up, I have my soft start procedure there to avoid the capacitors getting a high charge of current there. And I went into my software of the controller. I increased the timing a little bit for the soft start, right? It takes now about a second longer, and the problem was gone. You see, the definition for the word smart is very, very broad. I would not call it smart if a BMS cannot point out what was the problem, why it just has shut down something, right? But otherwise it's working perfectly now. Also here you can look into the cell levels, and yeah, now you can perfectly see how these jumpers are influencing cell level voltages. So if you're interested to see this in particular, that phenomenon, why, for example, I cannot use an active balancer here, I'm always asked why I don't use it. I can make a video and show you this now quite well with the BMS app, what happens exactly here in this pack, how the voltages behave over these jumpers here. After I saw the problems with the controller at the performance upgrade, I felt the need to go back to my PC and redesign some of my boards. The initial thought was to fix some issues on the controller board, which at the end was not really necessary, but still I have a new controller board here. And then all those troubles with the new big relay board, which is just a Chinese standard, I kind of had the idea to make something better out of it. And that's why I had the idea to redesign those cheap Chinese boards and make my own product series out of it. So, and these are the boards here in front of me, and let me show you exactly what it is, how it looks like, and yeah, maybe you find this interesting, and also maybe you find some use for it, because all these relay boards will be now available also here locally in Thailand on an online store, which I'm using already for the Watchdog, but also internationally on the Tindi store, which I'm using to sell my Watchdog there as well. So these are the new boards that I made. When I found out that I have a power problem on my controller board, I immediately went and designed the version 6. I thought that the version 5, which now still is inside the Powerwall, will be the short-lived board ever, but it was then actually not necessary to change. I am just using 2 buck converters there now. But this board is completely redesigned to use a 5-volt input already, and theoretically I could use 1 buck converter to supply the controller board and then also a relay board if necessary. Of course, it's not just the power rail which was changed. I also thought about what could be the next upgrade of the Powerwall, the final upgrade probably, and yeah, there is another digital potty connector now there, and also more I2C connectors. Why would those be necessary? Well, the other thing that I did was I designed a complete series of relay boards. I'm calling them the improved 5-volt relays. And yeah, why did I do this? Well, if you know the Chinese standard boards, you will see that they have quite some disadvantages, especially when it comes to these things we are talking about here, supplying them with external power, and also by how they are actually connected to the microcontroller, etc. It's all just by very flimsy male header pins, and then you have the choice to use even flimsier DuPont connectors, or you can solder on those pins whatever you want. But these boards here are solving all these issues. They are using the best available connectors here, the KF2 EDG connectors. You can remove the wires like that, so you don't need to unscrew all your cables all the time if you have to do something, change something. So I have designed 3 normal boards, a 3-channel, 5-channel and 8-channel, and yeah, all of these boards can be now directly supplied by 5-volt DC jack supply. Then we have the inputs are all now done by GST connectors, so they will not fall down or get loose. Otherwise, it's a standard principle. They are all optocoupler isolated inputs, and also if you look at the back side, we have isolation gaps between the AC and the DC. This is kind of taking care of all those negative aspects of those standard boards. And the price is still affordable. It's just the price difference is all just about what the components are better and a little bit more expensive. But then I have another one, and this is something you cannot get like this very easily. It's not a new idea, but it's not somewhere in mass production, something like this. You cannot buy it on Amazon or AliExpress or etc. This is actually an I2C board. So instead of having here now 12 separate digital inputs, we only have a serial connection here, I2C, I2C, however you want to call it, and then we have an extender IC here on the board directly. This is a 16-bit extender, and 12 bits are used for the relays here, and 2 I have used to add switches. Read out those switches. So that makes it a 12-channel relay board and additionally 2 switches. So here you can see the difference between my boards and the Chinese boards here. So at the Chinese one you have these absolutely crappy KF301 connectors. These are just meant for really small wires and not to connect anything bigger, what I'm using for my chargers, etc. And if you wanna feed in an external power, you have to actually remove this jumper here, and then you could kind of connect an external plus there, but you also have to get a ground to the ground pin here. And just as I said, all these pins, only these male headers, so it's not really easy to work with this. It's okay for the experimental stuff, but if you wanna work, do your IoT project, and you wanna connect some serious cables, then you go for something like this. And here you can see the 12-channel I2C board in action. I have my usual Arduino Nano here. The Nano only has 12 digital channels, so it would completely use up all channels if you wanna connect a board which does not have a I2C connection. And here we only use 2 analog pins which are there for the I2C and our VCC 5 volt and ground, and this goes just in here. We have our external power which you need for these big boards, otherwise, you know, there's too many relays to be pulled. And yeah, as you can see, I have a sketch running which is testing the individual relays now, and then later it's just activating all relays at once to see if the power is enough. And this is going to happen now. You see all relays are switching on one after the other, and we can still hear a click, and now all the relays are pulled. Yeah, as other upgrades, also this performance upgrade took some unexpected turns. Finally everything is working perfectly, and I must say the complexity of the system, as high it is at the moment, all those components are working perfectly together, and it's of course a lot of software work which is done there, that all of this can play together as it does. Yeah, we have another product in the store. So as I said, if you're interested, if you have some use for something like this, I would be really happy if you, instead of buying that cheap Chinese stuff, try and take a look on my designs. So thank you for watching this video. I hope you found it interesting. Please comment on the down how you liked all of this, and yeah, I would say I see you next time.